Good morning, students. This is Topic 7, Video C, Ionization Energy, Part 1. We continue our study of periodic trends. There are two we haven't looked at yet. Let's turn our attention to ionization energy. Ionization energy is the energy it takes to remove an electron from an atom. We can talk about the first ionization energy, the second ionization energy, and even the third ionization energy. Ionization energies have been measured and tabulated. Here is a table of ionization energies for the elements in period 3. Looking at the numbers, we can see that each successive ionization energy is larger than the last. I1 refers to the first ionization energy and is the energy it takes to remove the outermost electron from the atom. This electron is the easiest electron to remove. It takes more energy to remove the second electron, which is I2, and then more energy still to remove the third electron. The table continues onward with I4, I5, etc. This means that it is more difficult to remove successive electrons. When you remove electrons, the ion's radius decreases because there are fewer and fewer electron repulsions. To observe trends in ionization energy, let's plot the first ionization energy, that is I1, as a function of atomic number. We can do the same for the second ionization energy, and even the third ionization energy. Notice the large ionization energy in the I2 and I3 lines. To understand this, let's focus on the pink line. There is a big jump between I1 and I2 of sodium, and between I2 and I3 of magnesium. This pink line distinguishes the inner shell electrons, or core electrons, from the outer shell, or valence electrons. Remember that we are already familiar with this concept. The valence electrons are shown in the electron configurations, and the core electrons are represented by the inert gas. Core electrons are much more difficult to remove than valence electrons. Let's practice by looking at a typical exam question. Pause the video here and answer the question. Here's an explanation. Ponder this explanation and make sure it is clear. Let's take a moment to relate electron configurations, energy level diagrams, and ionization energies. Remember that an electron configuration shows all the orbitals that hold electrons for a given atom, and that each orbital has an energy that we can represent on an energy level diagram. For sodium, there are no electrons in the 3p, 3d, or 4s electrons. We're going to shrink the orbitals that matter and put a double slash in the energy axis to indicate that there is a big break between the energy of the 1s orbital and the energy of the 2s orbital. Now we draw a line that corresponds to the energy of the free electron on the energy scale, and put the sodium electrons into the orbital energy level diagram. We are going to imagine pulling the electrons entirely out of the atom, one at a time. If we do this, the removed electron is no longer bound to the nucleus and can be visualized as sitting on the free line. The electron configuration of the sodium +1 ion is now 1s2, 2s2, 2p6. The first ionization energy is the energy it took to kick the 3s electron to the free line. Let's draw the energy level diagram for what is now the sodium +1 ion. Notice that the orbital energies are a little bit lower than they were when we had the sodium atom, and the 3s orbital is gone. Why would the orbital energies drop a bit? In sodium +1, we have one fewer electron, and therefore fewer electron-electron repulsions, and so the orbital energies get a little more attractive. Attractive energies are lower in energy. Let's remove the second electron from the 2p orbital and make the sodium 2+ ion. The second ionization energy is much greater than the first because we removed an electron from the second shell. This means that the second ionization energy is going to be larger than the first ionization energy. When we removed the second electron, we reduced electron-electron repulsions. Now let's remove the third electron to make a sodium 3+ ion. We see that I3 is once again larger than I2. The difference in ionization energy between I3 and I2 is not as large as the difference between I2 and I1 because this electron came from the same p shell as the second electron. And once again, the energy levels are reduced. This is a general principle. As we remove an electron one by one from an atom, the ionization energy gets larger because each successive electron is more tightly bound than the prior electron due to the reduction in repulsions. When the successive electron comes from a new shell, the ionization energy increases dramatically, as shown by the pink line. Good morning, students. This is topic 7, video D, Ionization Energy, part 2. We have learned how to understand the trends in successive ionization energies in atoms. Now let's look at the first ionization energy as we go across a period. Although the arrow is pointing down, these atoms are increasing across period 3. We know that atoms get smaller as we move across a period, and so ionization energy increases. This is what we would expect based on the same electrostatic argument we had for size. You will notice that there are some exceptions to this general trend. Why is the ionization energy for aluminum smaller than the ionization energy for magnesium? Let's go back to the electron configurations to answer this question. The electron configuration for magnesium has 2 paired electrons in the 3s orbital. The aluminum configuration puts an electron in the 3p orbital. The 3p is typically slightly higher in energy than the 3s, and so it is easier to remove a 3p electron than a 3s electron. The electrons in the 3p orbitals are said to be shielded by the 3s electrons. Shielded electrons are less strongly attracted to the nucleus. What about the second exception? Why is the ionization energy for sulfur smaller than that for phosphorus? The electron configuration of phosphorus shows 3p electrons with the same spin in different p orbitals. The electron configuration for sulfur shows that 2 of the p electrons have their spins paired. Remember that it takes energy to pair electrons. We learned this when we studied electron configurations. So the sulfur p electrons are actually at a higher energy than the corresponding phosphorus electrons. This makes it easier to remove them. Let's practice interpreting ionization energies and relating them to energy level diagrams. Match the diagrams to P or S and then load electrons into their energy levels. Pause the video here and in your notebook show how the sulfur ionization energy would be smaller than the phosphorus ionization energy. Here is the solution. Sulfur has a slightly smaller ionization energy due to the increase in electron-electron repulsions that cause the 3p orbital energies to be higher than expected. So where are we? In general, ionization energy decreases as the size of the atom or ion increases. So ionization energy decreases as we go down a group and generally increases as you move across a period. There are 2 notable exceptions. The electron-electron repulsions in the 4th p electron as you go from group 15 to group 16 makes these electrons easier to remove. And the shielding of the p electrons in group 13 by their s electrons make the first p electrons easier to remove. Now let's practice by looking at an ionization energy graph for all the elements and see the trends. Pause the video here, maybe even print out the graph and identify the trends in your notebook. Here are the trends. First, group 1. It is a little difficult to see, but the ionization energies are generally decreasing. What about period 2? In general, the ionization energy is increasing as the atomic number increases. Now here's an exception that involves shielding. We are showing the beryllium to boron exception, but you might have identified the equivalent exception in period 3, shown by the purple line. An exception that involves electron pairing in period 2 is shown here.